Okay, good. Yeah.
Okay, so when you've all taken your seats, we're ready to start this session. And we start with Agnese, who will tell us some statistics on the gender situation in string theory.
Thank you very much. Thanks a lot for the organizers, also on behalf of the whole working group, to let us present some data. So first of all, who we are, why we are talking about GENET. So GENET is a permanent working group which is hosted by the CERN theory department. And the idea of this whole working group is to monitor the situation of women in high energy theoretical physics, increase awareness on gender issues in the field, improve visibility and presence of women in decision-making roles, and providing networking, support, mentoring, especially for the younger researcher. So we do a lot of activities, and I would like to point out the web page so you can take a look to our web page, and maybe some of you receive already the newsletter, which is sent every few months. So today I'm going to present some statistics, so something on data collection, and I wanted to introduce the other people who are in the working group other than myself. So there is Alex Belen, there is Yolanda Lozano, who is in the audience, and Silvia Penati. So the first thing that I would like to do, I would like to thank all the member of the community and of the GENET working group who contributed to collect the data. So maybe some of the people who gave us the data are sitting here, so thank you very much. This is the reason why we managed to collect this data. So just some background. So during the pandemic, we started discussing if we could at least have some kind of survey in the high energy community, because the last survey was almost 10 years old. And we felt that there was some urge to monitor the statistics and to collect new data, because we were always talking about, again, data which were pretty old. Opa, sorry, I think I did something bad. So now I'm talking about near extremal quantum field theory. Sorry. I don't know why I skipped doing statistics doesn't want to show up. That's okay, I can keep talking. Let me see if it's still, yes. I will do with the thing, it doesn't matter.
Yeah.
Maybe the clicker has some issues. Okay. Not even this works. Huh? Sorry. This doesn't work, the clicker. Maybe I can connect to Zoom with my laptop. Okay, but I can talk with that in the meantime. It's not a big issue. Okay, so we realized very soon after we decided to have this data collection that there are a lot of issues in collecting data. So the first one is that the theoretical high energy community is very large. Also, there is an issue between biological gender and gender identity. So each country, or at least each continent, has different way of collecting this kind of data or assessing them. Also, another very important point is that inside the GeNet working group, we are not experts on data collection, at least not all of us is expert on that. So this required a lot of discussion and a lot of time to understand that. And maybe the most important point is that we do it in our spare time and without any funds. So we didn't want to invest days and days to do that. So for this reason, we decided to start in 2024 with a smaller group. So what we did, we decided to focus, we decided to take the string theory community. So let me just clarify. I know that there is a big discussion on how to define the string theory community, but this was the best that came up to our mind. So if you have smarter ideas, please let us know later or just email us. So we decided to refer to the string theory community very broadly, meaning that a string theorist for us is whoever thinks is a string theorist, or whoever that, for instance, attends string conference or Eurostring conference. I mean, whoever thinks that is working on string theory. That was the easiest thing we could come up with. Thank you. This is much bigger than, yeah, okay, it doesn't matter. Okay. And then we restricted, instead of working globally, to some European institutions. So what we did, we asked a reference person in each of the blue countries. This was in 2024. And we asked them to fill a table with these entries. So you have to write down these numbers there. And sorry, this is, so the number, this is 2024. I'm presenting data from 2024, 2025. This is the number of scientists that we got number from, so it's 1,062, and you see that the ratio female versus male is 13%. That's okay, no, yeah, it's completely fine. I will manage with it. So here I just split the numbers with the different section that we got numbers from. So you see that, maybe you can see the, yeah. So you see in the first panel the PhD student, which is 16 versus 84%. Then there is a drop in the postdoc times, which goes to 11%. And then you see assistant professor goes back again a bit, 15%, but then there is a big drop, as expected in the full professor career. So then we did the same thing. Maybe you got an email to fill in a Google Doc. So this is what we did in 2025. So we just finished collecting data last month, I believe. So the new things, the novelty of this year is that we added a new category. So this is the reason why you see that the assistant professor is essentially a tenure track or non-permanent. So that's the reason why this starts at 0 here. It's not because there were 0 in 2024, it's just that we didn't have this category in 2024. And we added a few countries, for instance, Greece, Israel, and Ireland. And here you see, so this is not very hard to read. So this is the ratio of female versus total per position as a function of the year. So you see that there is slight increase in all the curves. And yeah, again, this green one is not because there were 0, just that we introduced it this year. But there is, yes, as I said, not very big change. So the biggest change is between the PhD part, but the most important point that I wanted to mention, that's why I would like to thank you again, is the fact that we increase by 50% the number of people that we reach. So we go from 1,000 to 1,500, so in 1 year. So again, thank you very much to everybody who answered. So we believe that it is extremely important to monitor this data. This is why I'm presenting them today, to at least show you what we do with the data, to reflect a bit on the situation, and maybe try to discuss also internally in your working place about this. And let me also tell you a bit what we are going to do, what at least we plan to do with the limited resources we have, meaning our spare time. We would like to monitor the data each year, similar to what we did in 2025. We would like to expand into other continents and include other data. This is much more complicated, so we need to have some structure, so we cannot use the same thing that we have. And also find a standardized framework to collect the data, also qualitative data, not only quantitative one. So this was more or less it about the data, but before finishing, I would like, on behalf of Irene, sorry, maybe this. Okay, so there is another activity which is not part really of Jeanette directly, because it's not meant again for women, but for underrepresented group, so in which women is also underrepresented. But the idea, maybe again, many of you already know it. There is a string theory mentoring program. So it's a mentoring program for people working on string theory across the world. So it's open to anyone, but targeted to the underrepresented group. Again, you can go on the web page. This is coordinated by Mariana Grania and Irene Valenzuela, who unfortunately had to leave, so you cannot ask her in person. And the applications are open. In particular, there is a strong need of mentor at any career stage. So in case you feel of becoming a mentor, just apply. So you can go to the web page and apply. There is time until mid next month, so September 14. In case, again, you want more information, there is the web page. You can just, I think, just Google string theory mentoring problem and you will get it. So that's the last thing I wanted to say. Thank you very much.
Thank you very much. Are there any questions on that?
So if I understood correctly, your goal is to inform the community rather than taking actions for the moment, right? Or you also implementing...
We don't have any power to do any action.
Yeah.
So this is just informing, because as I said, we asked the community to give us data, and we wanted to show you back, everybody back, people that gave us the data. We didn't decide yet. We are, I think, going to decide soon where we are going to publish this data, maybe on our webpage, but we didn't decide them yet because we finished collecting them really a couple of, maybe last month before the summer. So yeah, that's the idea of informing you about the numbers and the statistics.
Are you thinking about refining maybe the data in the sense of asking, the members of the community what they think or how they experience research?
Yeah. So when I said, for instance, qualitative data, it could be something like that. But, it's not very easy to collect data or even this kind of information. Yeah. We have a page in our webpage where people can send emails or something like that. So this could be one thing, but for the moment, we would like to take this data and try to monitor a bit the situation, mostly for the younger people, to feel that at least there is a community which is hopefully the most diverse possible.
So one very short comment, in addition to what Agnese has already said, is that on the GenHet webpage, there is a lot more information and also more discussion about actions that have or are being taken. So and if one is interested in that, then I really encourage everyone to sign up for the GenHet mailing list and get the GenHet information, which is published in a newsletter.
Yeah, there is also like other activities, conferences, maybe.
Okay, with that, I think we'll thank Agnese.
Thank you.
And due to the unforeseen presentation problem, we shift the schedule by 5 minutes ahead now. Yeah, we continue now, but it's shifted. Okay. Okay, so we had a preview of this already. And this is Near Extremal Quantum Field Theories in 2 Dimensions by Ankit Agarwal. Please.
Thanks a lot. Thanks to the organizers for giving me this opportunity to talk about this work that came out earlier this month with Arjun, Stefan, Daniel, Max, and John. Daniel is in the audience, and also some previous work that came out with Alejandra, Stefan, and Beatrix. Okay, so the motivation for this work comes from extremal and near extremal black holes. And as in Samir's talk, I am also going to define extremal black holes as black holes with 0 temperature, and near extremal black holes being the black holes with temperature close to 0. There are some interesting subtleties here, but it won't be important for this talk. So there are some universal features that extremal black holes exhibit. They develop an infinitely long throat in the near horizon region, and the distance from the horizon to any point outside the horizon becomes infinite. So the physics is completely decoupled between the near horizon region and outside region. And there is an ADS2 factor in the near horizon geometry for a very large class of black holes. And for very large class of asymptotics, like it could be asymptotically ADS, flat, DS. But this universal behavior doesn't seem to survive when you add any finite energy excitation. There are several reasons for this and several ways to see this, but probably the simplest is to realize that the distance from the horizon to any point outside the horizon now becomes finite, and the physics is no longer decoupled. However, this is not the whole story, and one can actually keep the effect of back reaction of adding the small energy order by order and still obtain a universal description to the leading order. And the universal description is given in terms of JT gravity, which is this 2D gravity model with dilaton coupled to the usual Einstein-Hilbert action in the negative cosmological constant spacetimes. And yeah, one can compute this action on shell and obtain the famous Schwarzian action, which is one-dimensional action with the Schwarzian derivative of some field f. And C is the coupling constant. This f is, it labels the reparameterizations of the boundary time. It famously captures the low energy dynamics of SYK model. And it's exactly solvable. In particular, the partition function is one loop exact, and it's given by this famous formula, where, as Samir mentioned, the partition function goes to 0 as the temperature is taken to 0, because beta is the inverse temperature. And there's this 3 halves, which is also, which is due to the presence of 3 zero modes. So this Schwarzian derivative is invariant under SL2R, and those 3 zero modes are responsible for this 3 halves. And this will be important later in the talk. Great, so I want to talk about near extremal quantum field theories. In particular, I want to ask the question, how does this universal behavior in the bulk, which is true in any dimension and for a very generic class of black holes, how does it manifest in the boundary theory? And there's, because of holographic duality, there should be a correspondence on the field theory side also. We will refer to this regime of quantum field theories as the near extremal or Schwarzian regime of the quantum field theory. And one thing we can already guess about this kind of regime is that we need to work with thermal QFTs in low temperature regime. And we also need to take other limits, but these things we definitely have to do. We need to look at the low temperature thermal field theories. Great, so in this talk, I will mostly be concerned with 2D quantum field theories. And we'll look at 3 different examples of 2D QFTs, which show this kind of behavior. One is the usual 2D CFTs, another one is warped CFT, and the third one is the Carolian CFT. A common characteristic of these theories is that there is a Virasoro factor present in the symmetry algebra, and there is also a notion of modular symmetry when you put it on a torus. So yeah, for first, 2D CFTs. It was shown by Ghosh, Maxfield, and Turiachi in 2019 that a very large class of 2D CFTs have this Schwarzian-like sector when you consider CFTs with large central charge and not necessarily large twist gap in the spectrum. And these results were shown to be in line with the near extremal BTZ black holes. And then a couple of years later, we showed that a large class of 2D non-unitary warped CFTs with large central charge also exhibit Schwarzian-like sector, which is the warped Schwarzian theory. And this theory describes the low energy behavior of complex SYK model. There's an extra U1 symmetry here. So in the partition function, instead of getting 3 halves, we get a 2, because now there are 4 zero modes. And this was also shown to be in line with the near extremal warped black holes, which are solutions to some 3D massive gravity models that Erika talked about, like TMG and NMG. And interestingly, only non-unitary warped CFTs have this kind of sector, and the unitary ones don't. Now, the Carolian CFTs, here we recently found that they also have a Schwarzian-like sector, even though the bulk theory, which is the asymptotically flat 3D gravity, doesn't seem to admit any black hole solutions. But we still argued that there are some solutions of these 3D gravity theories which are these O-plane orbifolds, which are going to be dual to these near extremal Carolian CFTs. Yeah, and in all these 3 cases, there is also a Cardi regime, which is different from this Schwarzian-like regime, but this is also universal. Great, so let me very briefly describe what are Carroll symmetries. As Emil already talked about it, I would just say that they are obtained as C going to 0 limit of Poincare symmetries, and they're relevant for flat space holography because conformal Carroll algebra in D dimensions is isomorphic to D plus 1 dimensional BMS algebra, which is the asymptotic symmetry algebra of asymptotically flat spacetimes in D plus 1 dimensions. And for this talk, we will just be interested in D is equal to 2. So the algebra is simply given by these commutators. First one is the usual Virasoro algebra, with CL being the Virasoro central charge. And there is this mixed commutator, and M's are the generator of supertranslations. It's a U1 algebra. In 3D flat Minkowski spacetime, there is a global symmetric group, which is ISL2R, which is generated by L0, L plus minus 1, M0, M plus minus 1. Yeah, this fact will be important, that there are 6 global generators later in the talk. Okay, so let me now define the partition function, the modular transformations for these theories, and everything goes very similar to 2D CFTs. So one can define the partition function in a very similar way to 2D CFTs with beta inverse temperature, H Hamiltonian, theta angular potential, J angular momentum. And there is also a notion of modular transformations, which is slightly different. So sigma and rho are the modular parameters, and sigma transforms in the usual way under modular transformations. But rho transforms like a vector on the upper half plane. And probably the most important fact to remember from this part is that the modular S transformation is given by this expression where sigma goes to -1 over sigma and rho goes to rho over sigma square. And one can also compute characters, just like one computes characters in 2D CFTs. One can define highest weight representations and primary states and everything and compute the characters, which are again given by these formulas. And the partition function can be written as a sum of these characters. Right. Now, what we want to ask is, are there any universal sectors present in Carolian CFTs? So for that, what we demand is, we demand that the partition function is dominated by the vacuum character in the S dual channel. And the reason that we demand that the vacuum character should dominate is because then we have universality. Then you don't worry about the details of the spectrum of the theory. And you can just rely on the global properties of the spectrum of the vacuum. So we demand that the vacuum character is the most dominant piece in the partition function. And it turns out that this happens in 6 different regimes or 6 different sectors. One is the well-known BMS Cardi sector, and there are others. But the most interesting one for this talk is the Schwarzian-like sector, where the temperature is going to 0, but from below. So it's negative. And there are other limits on the other potentials. And the assumptions about spectrum are that it's bounded from below. Yeah, there are, in all these sectors, at least in 4 of them, one seems to need negative temperature. And this is not very surprising because in the asymptotically, in the dual bulk theory, there are solutions called flat space cosmologies, which have negative temperatures. And they are supposed to be the dual to this field theory. So it's all consistent in that sense. And yeah, one can obtain this partition function for the Cardi regime, which is this guy, and in the cold sector, it's this one, but not very important. One gets the BMS Cardi entropy. Let me just jump to the main result, which is the partition function in this Carroll-Schwarzian regime. You see here that instead of 3 halves, now we have a 3. And this is related to the presence of these 6 zero modes that I talked about. And yeah, this is different from the usual Schwarzian theory. So that's one. And now I will go to the holographic interpretation of these results. So the holographic interpretation is given in terms of what's known as the O-plane orbifold. These are the orbifolds of flat Minkowski spacetime and solutions to 3D flat gravity. The metric can be obtained as certain limit of BTZ metric, which is, in particular, it's this limit, where the mass goes to 0 and the angular momentum is fixed. The metric of these O-plane orbifolds is given by this expression, and the Penrose diagram looks like this, where scry plus and scry minus are the future and past null infinities, and there are naked closed time-like curves in the geometry. So let me just finish by presenting what's going on holographically for the CFT and Carolean CFT side. So in the CFT side, this is the state space for asymptotically ADS gravity. The light-like directions represent extremal BTZ black holes. And so y-axis is mass and x-axis is the angular momentum. And the Schwarzian sector is present when we go to very high mass and very high angular momentum, such that mass minus angular momentum is close to 0. So basically going to close to near extremality. So you asymptote this light-like direction. That's where the Schwarzian sector is present. And for the Carolean side, the Schwarzian sector is present when you approach the x-axis. That's where the O-plane orbifolds are present. And you also have to be at large angular momentum. And this can be obtained as a limit from the CFT side. Okay, great. So let me summarize and talk about some open questions. So we saw that there are 3 different two-dimensional quantum field theories which admit a near extremal or Schwarzian-like sector. And this sector is different from the universal Cardy sector. A common characteristic of these theories is that they are all two-dimensional. They have a notion of modular symmetry, and there is at least one copy of Virasoro algebra. And the holographic duals for these 3 theories are as follows. The near extremal BTZ black holes are the holographic duals to near extremal CFTs, near extremal warped black holes for warped CFTs, and O-plane orbifolds for Carolean CFTs. Now, an important open question is, can one find such sectors in generic holographic QFTs, in particular in higher dimensions? And one expects that this should be the case, because as we saw on the bulk side, for any near extremal black hole in any dimensions, there was this universal behavior that emerged in terms of JT gravity. So there should be a holographic counterpart to that. And yeah, it would be interesting to explore that. Great, thanks.
Any questions, comments?
Yep.
Anki?
Perhaps a very simple question. In the modular transformation of the characters that you had tau going to -1 over tau and rho going to rho over tau square. But typically for modular transformation of Jacobi forms, the transformation is usually tau goes to -1 over tau and z goes to z over tau. I mean, but you have the square here. I mean, I was just wondering if there's any specific reason for
that
this.
Modular transformation that you mentioned, that happens for a warped CFT. But for Carolean CFTs, that's the one that seems to appear. I don't know if it is related to any Jacobi form, although we were able to find modular S matrices that relate the characters in the direct and the dual channel. It was some work with John Simon earlier this year. But yeah, it's the one that you mentioned is related to warped CFTs. But
Okay. Thank you.
Other questions? See no hands. Okay, let's thank Ankit Ben. And now we continue with the title, Recent Developments in ADS3 CFT2 Integrability by David Polvara. Please.
Does it work? Yes. Okay, let me thank the organizer to having given me the opportunity to speak here in this nice conference. And today I would like to speak about some recent work I've been done together with Alessandro Sfandrini and Sergei Frolov, which are both in the audience. In particular in the past 2 years. And what we did was to try to bootstrap the complete worksheet as matrix of superstring which propagate in this background, IDS3, in the presence of mixed flux. So let me give an overview of integrability in the context of ADS-CFT, which is our motivations. And as you probably know very well, there is this correspondence, which is ADS-CFT, and there is a particular limit of the correspondence in which the theory on both sides of this correspondence becomes integrable. So we have 2 parameters on the left-hand side. There is type 2b superstring theory, which propagate in ADS5 S5. And these 2 free parameters are basically the string tension and the string coupling. And on the other side of the correspondence, you have a connection with the other 2 couplings, which are the tooth coupling and the rank of the gauge group. And if you take the rank of the gauge group to becomes very large to infinity, so which is the planar limit of n equal 4, or equivalently you take G strings to be 0, so you consider strings which freely propagate in ADS5, S5, then you have an integrability descriptions of the theory, which means if you consider, and in particular in this talk I will focus on the left-hand side of the correspondence, if you consider these strings which propagate, the theory on the worksheet is a chiral models and as an S matrix which can be exactly found. And the first signals of integrability were found by Jominan and Zarembo here, I think, in Nordita in the 2002. So what is integrability? The idea is that you have a large amount of conserved charges, and in particular on the worksheet theory, you have this large amount of conserved charges, which forces the scattering to be diagonal and factorized. What this means is that if you consider 2 fluctuation which moves on the strings, which here I put like a red and a blue fluctuation with 2 masses, after the scattering, you still have the same masses for your particle. So if you can have in principle a supersymmetric multiplet, so you can have a reshuffle of particles, but you don't have, for example, productions of particles, so you still have the same type of particles after the scatterings. And then there is a systematic route starting from the S matrix, which means you consider the worksheet to be very large, and you have a notion of asymptotic state of your theory, to bootstrap the S matrix. And starting from this S matrix, you can try to quantize the string, which means first you go to large and periodic worksheet, and you do what is called asymptotic beta ansatz. But then if you want to quantize the string at finite length, what you need to do is to derive what are called thermodynamic beta ansatz equation, which keep into account basically also wrapping correction around this string also at finite volumes. And after a large number of, say, again, non-trivial steps, which is the derivation of Y system, to correlation, so on and so forth, you can end up to what is called a quantum spectral core, which is the modern method, say, more modern method to find the spectrum. Now, what we want to do is to repropose kind of the same approach for a different setups, which is ADS3, S3, T4. And in particular, in this case, you have half of the supersymmetry compared to ADS5, S5, and is a quite interesting since this background dates back to the early day of holography. And it was discovered by Cagnazzo and Zarembo that the family of principal chiral model and chiral model that lives on the worksheet of the strings are classically integrable. And in particular, in this case, you have also fluxes, differently from ADS5, S5. You have, in principle, 2 different parameters. One parameter is the amount of Nevers-Schwarz flux, which I label by K here. And the other one is the amount of Ramon-Ramon flux. So the first one is quantized, can be 0, 1, 2, and so on and so forth. The other one is a continuous parameter. And some of these backgrounds are well known. For example, if you consider pure NSNS flux and no Ramon-Ramon, then the theory on the worksheet is a Vezzumino-Witte model of level K, and the spectrum can be exactly found by CFT methods. On the opposite side, you can have 0 and SNS flux and pure Ramon. In this case, basically, the Zumino-Witten construction breaks completely. You cannot use RNS formalists to the quantization of the string. And in this case is where integrability really enters into play. And this, say, thermodynamic Betances equation and quantum spectral curve were derived independently by 2 different groups, one by Frolov and Sondrini and collaborator, and the other ones basically by Simone Camar, which is here in the audience, Nikolai Gromov, Cavaglià, Stefanski, Torrielli, and Volin. And basically, you can use both sides of this arrow are 2 separate sets of equations. Still, we don't know exactly how to match them, but can both be used to derive the spectrum of your theory. And then there is the most mysterious case, which is the case in which both the Ramon flux and the NSNS flux are different from 0, which is what I want to speak about in this talk. And in particular, what you have an action, is a nonlinear sigma model, in which what appears in this action is the tension of the strings, T, and a certain B field, which multiply basically this quantized amount of NSNS flux. And the 2 parameters I speak about before are this H and this K, which are both connected to the string tension. So these are my parameters of my theory. I want to describe the theory at any values of these parameters. And there is an interpolating family between the pure Ramon case and the pure SNS case. Okay, so this is the overall setup. So the plan of the talk will be to the derivation of the S matrix for my theory, both massive and massless S matrix, for the fluctuation of these strings, and then I will explain you what checks we did to prove, or at least have confirmation that our bootstrap results are correct. And then I will tell you about some future direction that we would like to pursue. Okay. So let me start with massive S matrix, first of all. So what we have some theory on the worksheet, and in particular we have 3 coordinates on ADS3, 3 coordinates on the sphere, and 4 coordinates on the torus. And what we want to do is to do some Lycon gauge fixing, which means you impose some Virasoro constraints, and we want to remove also all the redundant degrees of freedom of the theory, which means you don't do some conformal gauge, but we do some Lycon gauge. And after this Lycon gauge, the theory is not conformal anymore. You break conformality, and you also break Lorentz invariance. And in particular, if you start with 10 bosonic coordinates, you end up with 8 of them, which survive this quantization, which are all physical. You don't have any ghosts propagating on these strings. And if you study the supersymmetry realization of this theory, what you have that at the massive level, there are in total 8 massive particles in the theory. So this Y here and with Z comes respectively from the sphere and from ADS3. And on the other side, you have another supermultiplet of your theory in which there are Z bar and Y bar appearing. And the superalgebra, the gauge-fixed supersymmetry algebra of the theory is PS1, to the 4, which was derived in the past by Borsato, Olson, Sachs, Sondrini, and Stefanski. And in particular, there are some exact dispersion relation for the energy of your particles. So as you can see on the left-hand side, I label the energy of my particle by E left. And here appears both the amount of an SNS flux and both the amount of Ramon flux. P is the working momentum, and this one here corresponds to the mass of my particle, a certain quantum number that you can associate to the mass. On the right-hand side, you have exactly the same dispersion relation, but instead of having 1, you have -1. And what was done in the past was to find out what is the supersymmetry algebra of these models. And the idea of integrability is that if there is an S matrix which scatters the different particles of your theory, then this S matrix must commute with all the supercharges of the theory. So if you have some symmetries, and since the other symmetries must commute with your S matrix, which means that the S matrix is almost entirely fixed by just symmetry considerations. What is not fixed is an overall multiplicative factor. So of course, if you have two matrices that commute between one another, you can still multiply one of the two matrices by some function, and still these commute between one another. And to fix this orange parameter, which is called dressing factor, you need to add some extra physical input, like for example, unitarity, crossing, nice property under fusion. And this dates back basically to Zamologic and Zamologico when they attach this problem for a relativistic integrable theory. Here, I study a non-relativistic theory. And more specifically, what you have two different representations, one that I call left and one that I call right. When you scatter particle, you can have some reshuffling of particle in the representation. So if you start with two white particles, say, after the scattering, you can have that what then comes out are two particles of type Z or some other particle inside this multiplet, but you cannot end up with two right particles. So the scattering is completely elastic at the level of these representations. So basically you have four different dressing factors, sigma left, left, right, right, left, right, and right, left, which are not fixed. Because are this fact that you have in principle four possible different scattering between different representations. And what we did was to constrain basically these scalar factors, which I will not go enter into this particular discussion. Let me just say that there is a part of the scalar factor which is called odd for historical reason, which was obtained by Olson, Sachs, Rybchenko, and Stefanski. And what we did was to add to their solution the missing piece, which is what contain basically the BS dressing factor, the part which comes from Beiser, Eden, and Stabdacker for radius 5s5. Here we propose a generalization of these dressing factors also for this setup. And this is particularly interesting because basically it admits very non-trivial dynamics of a model. So okay, I will not go into it, but it admits a very interesting integral representation, for example, with Diego Hoffman, Maldacena, and Nick Dory. And to describe exactly what is this dressing factor, you should introduce, for example, what is the boundary between physical and unphysical region of your particle, where the energy is positive, where the energy is negative, and allow you to solve crossing. So once you find out what is the S matrix of your theory, you still need to use this S matrix to find the spectrum. And the idea is that we start from string region. So you take the limit in which the worksheet is very large, and you have a notion of asymptotic state, but then you want to go to the case in which the worksheet is finite, at a finite length. And to quantize the string, when you go to finite length and keep into account all the wrapping correction, you should derive the thermodynamic Betances equation of your theory. And Zamologico in 89 teach us that basically what you can do to quantize a theory at finite volume, this is equivalent to the quantization of theory at infinite volume but finite temperature, in which case the temperature is the inverse of your volume. So if you have a torus, in particular, you can associate it to one of the cycle of the torus to the time, and to other cycle the space, but you can also do the opposite, and there is a connection between these two sides. And the idea is that if you have a time and some space on the worksheet, you should do some double weak rotation, in which case you send the time to I sigma, to I space, and sigma to I tau. So you do this double weak rotation. And at the level of the energy of the momentum, this corresponds to send the energy to IP and the momentum to IE. So if you have some relativistic S matrix, by doing this double weak rotation, so suppose you have some relativistic special relation of a form E square minus P square equal M square. By doing this transformation, you still obtain the same type of dispersion relation. And the S matrix is still the same for a relativistic theory. But if a theory is not relativistic, like in this case, I have this complicated dispersion relation, when I do this double weak rotation, say I obtain a dispersion relation which is quite different compared to the original one. And the S matrix that you find on the string theory must be analytically continuous to this mirror region in a non-trivial way. So what we did was to study this S matrix both on the string region, what we call string region, and on the mirror region. And in particular, we checked that all the properties that were expected to be satisfied, because we knew the Lagrangians both on one side and on the other side, were actually satisfied. For example, if you consider parity, parity is a property which is valid in the mirror region, because if you consider you start with the Lagrangian of a string region, you do this double Wick rotation, so you obtain the Lagrangian of a mirror region. You will observe that sending sigma tilde to minus sigma tilde, the Lagrangian is left invariant. And you expect then the model should be parity invariant in principle, unless you have some anomaly at quantum level. But we don't want, so in principle we want to preserve parity for the mirror model, and you observe indeed that at the level of S matrix parity is satisfied. So what does it mean? It means that if you have an S matrix, you are reflecting in a mirror, you are just one dimension, so if you scatter P1, P2, this is equivalent to the scattering of minus P2, minus P1, basically. And this is a property which is satisfied at the mirror theory side, is not satisfied on the string theory side. What should be satisfied on the string theory side is a time reversal symmetry, basically, because sigma and tau are connected by the mirror transformation. And once you have the S matrix for your fundamental particle, and here I'm describing the scattering of fundamental particle, you can also derive what is the S matrices for the bound state. And this is also an idea that is very well known at the level of for integrable theories, which means if you have more particle which compose a bound state, so if suppose you have some bound state of mass m, which for fundamental particle m is just 1 or minus 1, but for bound state can also be plus minus 2, plus minus 3, and so on and so forth. So if you have, for example, m equal 3, means that this is a bound state composed of 3 fundamental particles. And to obtain the associated S matrices, you should multiply themselves as matrices of a fundamental particle composing the bound state. And the momenta of these constituent particles are chosen in such a way that the overall energy momentum conservation is satisfied for this bound state. But in principle, you have all the S matrices. And these are also obtained in a closed form in the paper, anyway. Additionally to the massive representations, which I was speaking before, there are also some massless representations. In particular, there are 2 massless multiplets, which comes from the fluctuation on T4 for this background. And this massless representation contains some index, A dot, which is an SU2 index. So you have 2 of these, basically, massless multiplets. And the S matrix contains a piece, which is the piece of a supersymmetric multiplet, which contains some reshuffle of a particle inside these supersymmetric multiplets, but also describe the scattering between the 2 different multiplets. So before I was saying that for left and right representation, for massive representation, we scatter completely elastically. In this case, in principle, you can have also some reshuffling between these 2 multiplets. And this SU2 S matrix perturbatively is expected to be just the identity. This is just a perturbative result. Apart from perturbation theory, you don't have any other confirmations. But our approach was to try to force this SU2 additional S matrix to be exactly equal to the identity also non-perturbatively. And the way in which we found this matrix for this massless fluctuation, basically starting from the massive one, and then taking the mass of our particle to 0. So in principle, if you associate one of the 2 massive multiplet, one of these 2 massless representation, and for the other one, the second massless representation, you take the m to 0 limit, and you obtain, starting from the crossing of this massive representation, the crossing equation of the massless representation. And okay, this was just a side comment, which I will not go into much detail. So once you have the S matrix, you still need to have, in principle, you can have some CDD ambiguity. So you're still not sure that the matrix is correct. So you still have a solution which satisfies all your symmetry requirements. But the solution in principle could be multiplied by some extra function which just satisfies all these requirements, in particular which does not affect, for example, parity, crossing equation, and all your symmetries. These are called CDD, and Roberto Tateo, I think yesterday, gave an overview of this CDD factor. For example, TT bar introduced this type of ambiguity. So what we need to do is still to try to have to be sure our answer is correct. We need to confirm this result in different perturbative regime. And in particular, what we did was to check that in the largest string tension, in what is called BMN expansion, the result agree with perturbation theory. And it does, both at 3 level and also at 1 loop, regarding the cut constructable part of the amplitudes. What does not, there is a disagreement for the part which is not cut constructible. And in this case, we believe that this disagreement is due to some counter term that should be added to the Lagrangian to have some, for example, to provide purely elastic scattering at 1 loop order. The other regime that we considered was a particular relativistic limit, which was studied in these 2 papers, both by me, Frollo and Sondrini, and also by Fontanella, Sask, Stefanski, and Torrielli, in which case, basically what we do is to consider the dispersion relation of our theory. So these are kind of very complicated dispersion relations. But then what you do is to consider the amount of Ramon-Ramon flux to be very small. So if you consider this H to be very small, it happens that this dispersion relation from this fluctuation, very ugly fluctuation dispersion relation, becomes basically a kind of a cusp. And you expand around the minimum, the global minimum of the dispersion relation, with fluctuation of order H, so the same order of the Ramon-Ramon flux. If you do so, you obtain that starting from this complicated dispersion relation, you end up with the dispersion relation of a relativistic theory, in which case, basically, you can solve completely the bootstrap in this particular relativistic limit. And this is really identical to what Zamologico and Zamologico did. It's very established approach, in which case you have a notion of what is a physical strip, rapidity, and so on and so forth. But then we want to compare that the S matrix that you find in this particular limit is the same S matrix that you obtain by taking the limit of a full solution of our full S matrix here. And this is a check that we did, and we obtain exact match for this particular case. So we believe that the answer should be correct. So what are the future directions? So one of the interesting things to be done at this point is try to take K finite and send H exactly equal to 0. So in particular, once you have a complete S matrix at any value of a Ramon-Ramon and Never-Schwarz flux, you can use the S matrix to find the spectrum. And there are some particular points in which the spectrum is known. And one of these points is the case in which you don't have any Ramon-Ramon flux, you just have pure SNS. And this is the Vezumino-Witten construction. So it would be interesting to see if at this particular point you can reproduce exactly the spectrum of the Vezumino-Witten model. And then the question is also what happens if you take, for example, k equal 1 and you consider a small amount of Ramon-Ramon flux, in which case there is conjecture, or there is a proposal for what should be the dual conformal field theories. And this should be the symmetric product orbifold theory, which I write here. It is by a paper by Eberhard, Gaberdiel, Nopakumar, and different groups have studied also deformation around the symmetric product orbifold point, and who be interested in trying to match what are these results from the worksheet theory point of view. Of course, you can try to solve a spectrum numerically at all value of H and K. This would be very tough and difficult problem, but in principle can be achieved. And also would be interested to try to derive, starting from our TBA equation for this matrix, what should be the quantum spectral curve equation. This connection is still lacking also for the pure Ramon-Ramon case, so this is still work in problem also for the case in which K is equal to 0. But is for sure a very interesting direction, and to have a completely control on the numerics. And then in general, you can try to promote T4 to some more generic manifold. For example, S3S1 is also one of the manifold which should be integrable, and Fiona Seibel yesterday mentioned about this. So there is an entire class of integrable theory and the formation of this integrable model which still remain to be explored at the quantum level. This is one of the most simplest examples which we would like to solve completely. So I will conclude here. Thank you for the attention.
Thank you. Questions and comments? Welcome. Touch. Okay, let's then thank David once more for the nice talk.
Hello? Yeah. Seems to work.
So
1 second.
in 1 second, we'll hear.
All right.
We'll hear Truls Harmark talk about gravitational solitons and non-relativity string theory, please.
Yeah, thank you. I should say apologies in advance because I woke up with a major cold, but I hope it will not interfere. Let me see how this works. Yeah. I will talk today mainly about this work here, but it will also be related to, and this is with Johannes Lahnsteiner and Nils Obers. But it's also highly related to some previous work, and it's highly related to Siggy's beautiful talk as well. Let me see if this works. Yes, all right. So just a very sort of broad introductory slides. So I think, of course, since we are at Eurostrings, we would all like to understand quantum gravity. And this is sort of where you unify relativity and quantum mechanics and gravity all in one beautiful package. But it's not super easy to understand. So one can take certain limits and try to get a better handle on things. And one of the interesting limits one can take is to take the speed of light to infinity. So you get rid of relativity and instead do non-relativistic quantum gravity. And then maybe you can learn something about quantum gravity, which is hard to do in the full theory. So a way to approach non-relativistic quantum gravity is to consider certain BPS modes in string theory. This might seem surprising if you haven't thought about this, but you can start with basically just flat space, but with a circle, and then you could take a BPS state where you have corresponding to momentum along that circle. If you now want to focus on modes that lie just above this BPS state, that's what I tried to illustrate on this energy ladder here. So you want to focus on modes that are near BPS, where this W is sort of the quantized momentum. Then you can do that by changing coordinates that focus on energies that are really close to this BPS state. So if you do this coordinate transformation, then you can see that you get the energy minus the BPS energy. And then if you take C to infinity, then you basically take a decoupling limit that really decouples these modes from all the higher lying inner modes. And this is actually nothing but a DLCQ limit, which is famous also from, for example, the BFSS matrix theory story, etc. And one of the weird things of BFSS is that it somewhat seems to involve compactifying a null direction. And this has sort of given it a little bit a slightly bad reputation that it seems a bit a singular or not really geometrically not really very well-defined limit. However, if you take a t-duality along this compact direction before you take c to infinity, then you can then you get this background instead with a critical electric B field, and now the c going to infinity limit has transformed itself to the so-called non-relativistic string theory limit. In this case, in flat space. And here you can actually, as I will show you in a moment, make sense of the geometry. The point is just, it's not geometry as we know it, but it's a non-Lorentzian geometry. So basically zooming into this BPS point give you non-Lorentzian geometry, and that's also the what Sigi was telling you. This was the story 25 years ago. Since then, we have learned a bit more about how to take this limit more generally, not just in sort of around flat space, but you can also do it basically in a general curved background. So there's some details here, but it's not so important, the details. How you formulate this, that's more like if you really want to work with it. But the point is that you split the metric and the Calpomon field in a longitudinal part and a transverse part, such that the longitudinal part is designed to give you a critical electrical B field when you take C to infinity. And if you do that, then you can take your favorite relativistic string Nambu-Goto action and take this limit, and then you get a finite answer, which is this. And again, the details are not so important. It's more a sort of a message that it gives a finite action. But this action is no longer with a relativistic target space. It's with a non-relativistic target space. The so-called torsional string Newton-Contang geometry. And the point here is that you split up the longitudinal part and the transverse part, and then you even get a part from the Calpomon field that all goes together in some beautiful geometric package that you call torsional string Newton-Contang geometry. And among other things, you can see that the speed of light is actually infinite in this transverse space, and you get some Galilei-type boost that makes the part with the longitudinal and the part with the transverse written here. So this is a new geometry which is not relativistic. So this above limit is quite amazing, but it has also some limitations, or it hides some crucial things, because it's not for sure that any string background you want to look at, relativistic string background you want to look at, actually fit into this limit. So this was one of our motivations for our study, that we wanted to try to take actual gravitational solitons of relativistic string theory and see if we could take this limit. And probably I don't have to say this, but gravitational solitons are quite important in string theory. We have been recognized that for the last 35 years or so. So they're consistent, give you consistent target space backgrounds of string theory. You can use it to study certain non-participative physics of string theory, halography, obviously, and also thermal physics. You can learn about with, say, black brains, for example, or black holes. So let's see how you can find gravitational solitons in non-relativistic string theory. So we were, in a way, very simple-minded about it. We simply wanted to try to repeat the procedure that was done in flat space, but now for curved backgrounds. So we considered a particular class of solitons for which you have a Poincaré, 1+1 dimensional Poincaré symmetry along the directions here called t and x. And this is what we think of as the longitudinal part of the solution. And then we do this coordinate transformation that was also on one of the first slides. And we do a t-duality after the coordinate transformation. Then we should get a finite C soliton that should have the correct scaling in C in this parameter we take to infinity. And then we finally take C to infinity, and then we should get the gravitational soliton. And this works quite well, at least in some cases. So if you take a dp+1 brane, again, the details are not super important here, but it's just to show you something. So +1 is for this direction big X here, because we want this 1+1 dimensional Poincaré symmetry of the D brane. So here we have 1+1 dimensional Poincaré symmetry. Then we do this solution generating technique, and out comes a non-relativistic string theory geometry, which looks like this. And since you have to do a t-duality along the way, this dp+1 actually become a dp brane in non-relativistic string theory, which is now smeared along this direction v, which is longitudinal to the strings. So actually this is, in a sense, a transverse dp brane because it doesn't share this v direction with the string. And this was also sort of predicted that this solution should exist from open string point of view, at least in the probe limit, but this is in the back-reacted, this is for the back-reacted dp brane. That was not found before. And after our paper, Chris Blair figured that this actually is a half BPS solution in non-relativistic string theory. Then, since we know of the importance of gravitational solitons, we can try to think of some of the same things we have been doing in relativistic string theory. So one thing is to take a near horizon limit, and the cartoon version of a near horizon limit is simply just to say that this part here blows up so that you emit the one. And that is what gives this near horizon dp brane geometry in non-relativistic string theory. So an interesting thing we observed was that if p is equal to 3, so you have a d3 brane in non-relativistic string theory, then the dilaton remains constant. So we think perhaps this could give rise to a new holographic correspondence. We haven't had time to explore it yet, but we are planning to do it. And what's interesting, we think at least, is that this is really a gravity background in non-relativistic, in some version of non-relativistic gravity. So if there is a duality there, it's really a background in non-relativistic gravity and most likely some non-relativistic field theory as well. So on the field theory side, as far as I know, this field theory hasn't really been written down, but there's some studies of this limit by Siki and other people. But you can also play other games with this solution. You could try to think of what happens if you put a temperature, right? So you can put this blackening function inside the DP brain. So you get this, you modify the solution with this F function, and then see what happens. And I think I forgot F in the transverse part, but it doesn't really matter for the for what I'm gonna say. So if you try to go through the same thing, then you see that after the T-duality, you get this background here. But now you cannot really, at least not if you have F different from 1, take the C going to infinity limit, because this B field is not critical anymore. So on the face of it, it looks like you cannot really have a black DP brain in non-relativistic string theory. And this we found very interesting, because how should one interpret that? Does it mean that you cannot have horizons in non-relativistic string theory? What happens if you turn on the temperature in the theory, etc.? So there's something here that we really would like to understand better. Then one can, of course, also play the same game with other solitons, such as the NS5 brain, where we did the same thing and found rediscovered a previously found solution as well. But there's also cases where if you try to do what I described, looks like on the face of it, like it doesn't work, or not the way one would expect from what I said. So one case is if you take, if you go back to the original winding mode. So this BPS momentum mode, I forgot to say that, but after the T-duality, that becomes a winding mode. So this solution with a critical B field has a winding mode. And of course, for a low winding mode, if this winding number is low and the string coupling is small, this doesn't back react. But you could imagine you turn on the string coupling and then you have a very, very high winding number, and then you get a back reaction. So what happens? Well, then we, by the rules of relativistic string theory, we get a F-string soliton. So what happens now if we take C going to infinity? And this at first seems a little bit of a mystery, because if you take C going to infinity, you notice that the coupling to gravity becomes infinitely large. So how do you interpret this? Well, that's precisely a near horizon limit. So a near horizon limit is nothing but having that the coupling to a source becomes so large that, in a sense, the source is everywhere in your space-time. So in other words, we get the near horizon limit of a F-string. So that means that this C going to infinity limit in this case, which we previously called non-relativistic string limit, is precisely a near horizon limit. But what is the interpretation of this? Because now we have gone from, something I called non-relativistic string theory to this background here, but this background is not a geometry in non-relativistic string theory. This is a background in relativistic string theory. So is there something, does this invalidate the whole theory, even if we have that it's been shown that non-relativistic theory is UV complete and unitary? I mean, what's going on? And then we have to go back to the late 90s and think a little bit, because actually the famous IMSI paper tells us that the validity of this near horizon F-string requires the curvature length scale to be larger than the string length. And one can use the tools learned back then to translate that into a condition on the energy of the worldsheet theory, which looks like this. So our interpretation of this is that this near horizon solution, near horizon background is a description of non-relativistic string theory, or rather the worldsheet theory of non-relativistic string theory, when the coupling is sufficiently strong. And in fact, you can see if the string coupling here would go to 0, this would become so large that for finite energy, this energy range would not really be there anymore. Or, yeah, you can play the same game with the winding number. So that's our interpretation. And we can make a further argument for this by looking at non-relativistic string theory, because an interesting thing with non-relativistic string theory is that if you consider multi-string states in the limit, thank you, you can convince yourself that since all the strings are parallel to a particular direction on which there's a winding number, and since this winding number has to be fixed, then the multi-string states are actually partitions of this winding number. And I just try to illustrate this if for the particular case of winding number equal 3. So then there's 3 cases that you have to consider. And this you can actually translate, again, going back to the 90s, to a matrix description. The details are here if you're interested. And this is nothing but what Lubos Model and Robert Dijkgraaf, who was here, and Herman and Eric Verlinde did in 97 when they found matrix string theory. So in other words, matrix string theory is basically non-relativistic string theory in type 2b flat space. This was already, I should say, recognized by several people. But here it's this is the statement, yeah. But then if you go back to Dijkgraaf et al.'s paper and consider the interactions on the non-relativistic string worldsheet, then there is this twist field operator. And you can then convince yourself that this means that the non-relativistic string worldsheet theory is weakly coupled when you have sufficiently low energies like this. And this is precisely the opposite requirement of our near horizon requirement. And of course, this is, in a sense, no surprise if you remember the lessons of what people did in the 90s. But here we sort of found this to be true also for non-relativistic string theory. So it sort of gives the non-perturbative completion of non-relativistic string theory. Yeah. So this also opens up, I think, for some new ideas, new things to explore, because this action here that I was highlighting in the beginning of the talk, one could actually try to find a matrix-valued version of this action, because in a sense, this action is when you only have one string, but there should be a corresponding action for multi-strings. So it should be possible to write down, a version of this action where the transverse fields are matrices. And this should give you access to a quantum geometry of non-relativistic string theory. And this would actually mean you, in this sense, maybe can go a bit further than relativistic string theory and learn about some parts of string theory that is more difficult in the full relativistic string theory. And one could also dream about combining this, for example, with this version of holography that I highlighted before. And for example, also study how holography works with an infinite speed of light. And then my last slide, I just wanted to highlight the connection to Siggy's talk, because all this is part of a broader network of BPS decoupling limits. And you can think about basically all the U-dual orbits of the DLCQ. We started doing that 25 years ago, and now it looks like we are finally trying to complete it. Especially, I want to highlight some of these two papers. There's also more, but for sure these two papers on this by Blair, Siggy, and others. So there's the non-relativistic string theory for the F string. There's the BFSS. It should have been the matrix theory for the D0 brane. There's Maldaceno's decoupling limit for the D3 brane. And then there's also other cases, and then you can take multiple decoupling limits as well. And then we are hoping to make a even more systematic exploration of all this in an upcoming paper with Jan de Boer, Niels, and Siggy. And then there's also another case where it seems to work a bit differently. So this Maldaceno decoupling limit is in the Poincare patch, gives you ADS shift T in the Poincare patch. But if you think about the global patch, it's connected to something called spin matrix theory. And then things work a little bit differently with these non-BPS decoupling limits. Thank you.
Thank you very much. Are there questions, comments for Troels? Can't see any.
Thanks, Troels. So just a quick, so what kind of backgrounds do you expect for the bulk theories to have? So is there some kind of non-relativistic limit of ADS that you expect to appear?
You mean for the this holographic case or what?
For the non-relativistic holography.
Yeah. So that it's I mean, basically you have a combination of having a D3 brane, and then you have a electric field where the spatial direction is transverse to the D3 brane. So it's actually a quarter BPS state seen from the relativistic string theory. And I mean, the background I wrote was the one I showed you, but we still have to explore it. Yeah.
There are no more questions?
I think Laura had a question.
No, he
maybe.
changed his mind.
Oh, okay, fine.
Okay, let's thank Troels once more. And now it's coffee time, and we reconvene in 20 minutes.
Sorry?
I don't know if it needs to be charged, but I'll just put it.
Yeah, it's better safe than sorry. Yes. Oh man.